Hello everybody, this is New York City Bobby with my latest project, a Chinese dragon boat. It's back from its second test voyage and let's put it this way, the maiden voyage almost resulted in this boat being sunk. It got close enough to shore just as it was going underwater and I was able to pull it out. Since then, I've made some modifications to address some of those issues from that initial maiden voyage, and I'll go over with you now exactly how this boat works and how it was constructed. The Dragon boat sports a dragon head in front and, of course, a tail in the back. It has a rudder in the rear controlled by this servo. It has 10 paddles on each side capable of rowing the boat forwards or backwards. This small structure in the back is called the doghouse and protects the electronics. The boat is powered with a 3S LiPo battery located in the front. The rowing mechanism is rather simple, so let me explain how it works. In order to row, the paddles must move back and forth and also come out of the water during the return stroke and plunge back into the water at the beginning of the power stroke. To move the paddles back and forth, I decided on using a mechanism called a slider crank. The paddles are moved in and out of the water using high-speed servos. I will discuss the left side of the boat as the right side is simply the same mechanism mirrored. As you may expect, the slider crank mechanism consists of two main parts, a crank and a slider. A link connects these two components. Here in the rear is a DC brushed motor. It's ideally suited for this project as it has a double-ended shaft that sticks out both sides. A crank is attached to the end of each shaft. A plywood link painted yellow connects the crank to the slider. In this boat, the slider is the entire frame that houses the paddle assemblies. The cross pieces that hold the rails have two linear bearings mounted near the bottom. These bearings allow the entire frame to slide freely on two 5mm rods mounted toward the bottom of the boat. The motor is controlled by a brushed motor speed controller, and when turned on, the entire frame will move back and forth, taking the paddles with it. The stroke is determined by the length of the crank. In this case, the crank is 1.25 inches long, so the stroke is twice that, or 2.5 inches. Each paddle assembly is attached to the rails by sliding a carbon rod through the hinge holes. This allows each paddle to swivel. At the top of each paddle is an end cap that allows a brass rod to slide through. This long rod goes through all 10 paddles and then is attached to servos in the front and back via servo arm extensions. When these servos are activated, they cause the paddles to swivel, lifting them out of the water. When the servos return to their initial position, the paddles are plunged back into the water. Two limit switches mounted to the base are activated by a small cam attached to one of the cross pieces. When these switches get activated, it tells the Arduino when to activate the servos and lift or lower the paddles. These switches are on slotted mounts so that the timing of the paddles can be adjusted. To go backwards, you merely have to reverse the logic in the Arduino code. Now with everything powered up, let me demonstrate the mechanism. I am using my Turnigy 9XR DSM radio. The throttle stick controls the speed controller, the aileron stick controls the rudder, and the gear switch controls the direction of rowing. Under the doghouse are the electronics, which consists of an Arduino Nano, the RC receiver, and a proto board for making connections. You can see and hear that the mechanism is pretty loud. Also worth noting, the maximum speed that you can row at is mainly limited by how fast you can move the paddles in and out of the water. If this doesn't occur fast enough, the paddle will end up entering the water too late, and you will have wasted a good amount of the power stroke without having generated much thrust. That motivated the need to have high-speed servos. Before building the hull, I decided to make a small section of it and test for stability. It was loaded with penny rolls until the proper waterline was reached, then tested for stability in my bathtub by tipping it back and forth. The stability seemed acceptable, so I built the final hull. The hull is made from Dollar Tree foam board with the paper removed from both sides. The construction takes place upside down. The long deck piece was laid down on the bench top and formers were hot glued in place. The formers are doubled in the middle middle and the ends. The bottom piece consists of 2 sheets of foam board joined in the middle. The sections that require a curve were pre-formed by rolling the foam over the edge of a table, a common technique used to give foam a memory. It was all hot glued together and held in place with masking tape until dry. At this point, I thought to fiberglass the hull, but not having a large enough piece of fiberglass cloth, I looked for alternatives. I came upon a video that talked about the poor man's fiberglass. This technique involves using a cloth like linen or canvas and applying wood glue to it instead of epoxy resin. I tried it out on the test section I had built, and after letting it dry for days, I was able to peel it right off. So I shopped for fiberglass and bought a sheet of 6-ounce fiberglass cloth, 1 meter wide by 2.7 meters long for $19. I happen to have Easy Lam epoxy resin that is at least 30 years old. I did a pre-test and it got hard as a rock, so I used it on the hull. It came out great. The hull was flipped over and most of the deck was cut out, leaving a large open volume. The hull looks like a long loaf of bread. I am way out of my element trying to make the dragon head and tail. Thanks to the YouTube channel BM Sculptures, shout out to Blake, I used his technique of creating profiles to aid in carving out the figure. Lucky for me, these dragon boat figures tend to be on the cartoony side, and a good paint job can really save you. I traced out a profile of the dragon head and cut it out using a Dremel tool. This was cut out of a piece of 1/8 inch plywood. It was glued to a base whose shape was that of the hull cross-section, and then a large piece of blue foam was glued to one side of the profile. After carving, another piece of blue foam was glued to the other side, and the carving was completed. The dragon's teeth were made from sharpening a dowel and a pencil sharpener and cutting it off and gluing it into position. The tail was made in a similar technique, with its profile being made out of a piece of cardboard instead of wood to see if it would work just as well and save money, which it did. A little template cut out of an index card was created for drawing the scales. After the white base coat was painted on, each scale was hand-drawn on and then painted. The paints used were acrylic paints from Cali Art. They are very nice to work with and reasonably priced. After painting, the pieces were coated with epoxy resin and then several coats of water-based Varathane was applied. The mechanism is almost entirely 3D printed. The side rails are in 4 pieces, glued together using CA cement. The cross pieces house the linear bearings near the bottom. They also receive the screws used to attach the rails. The 3D printed layers were splitting as the screws went in, so button thread was wrapped around these areas and CA cement dripped over the thread. This was effective at preventing splitting. Each oar assembly consists of 5 parts. The oar is slid into the oar holder, the end cap is applied, then a pin made from cutting a paper clip is slid in to lock the 2 parts together. Then a thin slice of heat shrink tubing is shrunk on to capture the pin from coming out. Each oar assembly is attached to the rail by sliding a carbon rod through the hinge holes. 5 oars are held in by each carbon rod. A small strip of electrical tape holds the rods from sliding out. The links and the cranks are made of wood, although the crank were eventually swapped out to be made out of aluminum. The motor mount is made from plywood, and all these parts, along with the servo mounts, are screwed down to a very straight piece of wood. The rudder is made of curving 2 sheets of balsa wood around a brass tube. This gives a natural airfoil shape to it. As mentioned earlier, the speed that this boat can go at is limited by how fast you can pull the oars out of the water and get them back in. I realized that the standard servos I was using were not fast enough to allow for fast rowing, so I invested in fast servos. When I observed them in real time, they didn't seem to be much faster, but in slow motion the speed is very noticeable. In order to ballast the boat and get it to the correct waterline, I decided to buy 8mm steel balls. They were poured into the bottom of the boat as shown here. It takes about 7 pounds of weight to do the job. The rowing mechanism was put in place and the boat tested in the bathtub. Everything looked good, so it was time for the maiden voyage. Spoiler alert, I created a positive feedback loop. The balls were not anchored in place, but I figured the pond was so calm. I expected no major disturbances, and I also didn't really see where the balls could move to. Big mistake. Should the boat tip a bit for whatever reason, say a small little wave, that will cause some balls to shift in that direction, making the list a bit worse. This will in turn encourage some more balls to shift that way, and before you know it, the boat is really listing uncontrollably to one side. This is exactly what happened, and the boat almost sank on its maiden voyage. To address the stability issue, I believe that anchoring the steel balls in place would have probably provided enough stability, but seeing how much electronics are on board the boat, capsizing is really unacceptable. I happened to find a steel pipe in a dumpster, loaded it up with balls, and screwed it to the bottom of the hull. The ends were capped off with a cork from a wine bottle, and then foam pieces were rounded off and attached to the ends to reduce drag. This pipe weighs approximately 4 pounds and displaces about 0.8 pounds of water, meaning I still needed to add about 2.5 pounds of balls to the bottom of the boat in order to achieve the proper water line. Small compartments were made to hold these balls under the rowing mechanism. They were capped off with thin cardboard lids painted with the water-based Varathane. Although the maiden voyage did not last long, it was apparent that the boat was rowing very slowly. I also decided to enlarge each oar by gluing a small piece of balsa wood onto each oar, making it about 3 times larger in area, hoping that might increase speed. Here we are, it's June 27th, 2025. We're going for our second test of the Chinese Dragon boat. Got it loaded up on my cart. We're on Freedom Place again. Talk about that in a minute. And we're just going to take this little back street because it's nice and empty. And we'll work our way back to Central Park and hope for a better experience this time around. So this is why it's called Freedom Place. There's a plaque at the corner of 70th Street and Freedom Place dedicated to James Chaney, Andrew Goodman, and Michael Schwerner. These were 3 young civil rights activists who went down to Mississippi to register blacks to vote and were ultimately shot and killed by the Ku Klux Klan. And I believe the local sheriff was involved in the murder as well. The movie Mississippi Burning was made kind of loosely based on this historical incident. Chaney was black, Goodman and Schwerner were Jews, and it was really a shock to the world when those bodies were found, because a lot of people don't even know Freedom Place exists, much less why it's called Freedom Place. Here we are entering Central Park at 72nd Street. Here's a classic horse-driven carriage. Over there, that building with 2 towers is an amazing building on Central Park West called the San Remo. This building is the Dakota, where John Lennon lived, where Rosemary's Baby was filmed. John Lennon was shot right in front of that building, and right over here to the right, through these trees, is Strawberry Fields, which was set up by Yoko in honor of John. There's always somebody singing Beatles songs here, so you could hear it in the background. And we're gonna head down this hill and make it our way to the pond. This tree has an amazing, I don't know what that's called, an eye or something like that. Whatever it is, it's an amazing thing. I go by this tree a lot. I've just seen this thing get bigger and bigger over the years. This is the gorgeous Bethesda fountain. Really, truly a beautiful, beautiful fountain. This thing rivals anything I've ever seen in Europe. And of course, Central Park is so gorgeous. And it's just such a beautiful scene. And then underneath here, this walkway goes underneath these tunnels that have the most gorgeous Islamic kind of art inside it. It's just incredible stuff. All right, here we are back at the pond. It is a Friday. It is a overcast day. We just got over a heat wave a day ago. It had been 95 followed by 99. I think we had 2 days of 95, then 99. And then yesterday it broke. Today's probably in the 70s. I have my shorts on because it is possible I may have to go in for this boat if it flips over. So just to quickly go over what the issues were last time. The boat was unstable. When I first put it in the water, it was stable for a little while. I started rowing it. It went incredibly slowly. and then it started to list to the right. Eventually it became so listed over to the right that it was about to sink when I was able to haul it back in. It wasn't too close, you know, it was pretty close to shore when that happened. Anyway, so we need to have, hopefully we address the stability issue. I know the boat's not super stable, but it's better, so hopefully it'll be okay. The speed at which the boat was going because of the rowing might not be that easy to fix. This thing just might never go fast, but I did make the oars about 3 times bigger in area, so maybe that will help. So we'll see how this goes. Well, here's the Dragon boat floating in the pond, having just put her in after the mods, and it is quite stable. I'm very happy with that. So here she is taking her first rows after the mods, and she's going pretty good. Slow, but good. Here it is coming toward me. You can see the dragon head looks pretty cool. Let's try to put it into reverse. Now I got it in reverse. Yeah, reverse definitely works. Alright, I'm gonna go forward again. Here's a view looking down the length of the boat as it rows. You can see the brass rods that go through the paddles shake so much. They're so long and thin, and I don't really know if the shake matters that much because it does seem to damp out before it plunges back into the water. But man, it is pretty cool to watch in slow-mo. Well, there you have it, the Chinese Dragon boat. I thought it came out really, really well. I was very happy with it. It, of course, is a unique kind of a boat to bring to a model boating pond. It got a lot of attention when I was there, and people were kind of excited about seeing it row. Of course, the only problem is it goes slowly. Now, I don't mind that it goes slowly, but it really can't even overcome a light breeze. And then, you know, when that happens, the Dragon boat will end up getting blown wherever the wind takes it. So the question is, how can I improve the performance of this boat without doing a major redesign? One of the things is, I noticed the paddles are only going in about 2/3 of the way. And there's a pretty good amount of clearance when they come out of the water. So I could easily reprint these paddles and make them longer and pick up some more area. Now, when I made the modification to increase the area of the paddles, I had to increase it on the outside only. The mechanism is too close to the hull of the boat right now to make the paddles go any wider in that direction. I could easily reprint up these cross pieces, widen the entire mechanism, and then the oars could, or the paddles I should say, could be symmetrical. But that's a lot of work. I'm not sure how much that would really matter. Another thing to consider is the actual shape of the paddles. Right now they're just flat. I think in a traditional Chinese Dragon boat they are pretty flat, but I think if they were spoon shaped it might work a lot better. So I'm going to do some experiments just dragging spoons in different shapes across water and see if I can get an increase in force. It would be pretty simple to reprint these paddles up, making them more spoon shaped and making them a little bit longer so we get more area in the water. The other thing I noticed was when the boat is rowing, it produces an amazing amount of interesting waves on top of the surface of the pond, and I'm wondering if sometimes those waves might interfere constructively with each other, and at other speeds they might interfere in a destructive manner. So I'm wondering if there's a sweet spot for the speed at which, it's possible going higher speed might actually result in the boat moving slower. So I think I need to address that also. That's kind of an interesting thing to study. And the other thing, I was talking to someone who does row. I don't do any rowing, and of course he said something really important to me, and that is when the paddles go into the water is critical. If they go in when the stroke has just reached its front limit, when they plunge into the water, they may actually break the boat and slow it down. So they really need to enter the water with them moving, and I need to check that. Now that's something I can adjust, because I can slide those limit switches around and change the timing. But these are all things for the future. I don't know how much time I'm going to be spending on this in the near future, but those are things I hope to work on, and we'll give it another test. So just want to thank everybody out there for watching this video. I hope you enjoyed it.